what speed would all those molecules be going if it was absolute zero?
An average of 0.
They would all be going 0. Not an average of 0, they would all be going 0. So, all the molecules would be going the exact same speed. In fact, this graph would look like this. Now, we call all these possible speeds that molecules can be going, we call them microstates. Now, a microstate is just a different place. This particle is going faster than this particle is going faster than these particles. So this has a much greater possible number of microstates. What if that gas was not 25 degrees? What if that gas was 100 degrees? So here's 25. What would the graph look like if it was 100 degrees? Start at the same place because we still have some going crazy slow. It looked like this. Which one has a greater number of possible microstates? The 25 degrees or the 100 degrees? 100 degrees. Okay? So, we call this idea of different numbers of possible microstates. This lends itself to, I'm trying to use something that doesn't exist right now. This lends itself to something we call entropy. So, entropy is S. Don't ask me why, never have understood. Entropy is measured by S. Just like enthalpy is measured with H. Another one I don't quite understand. But entropy is S, and it's the amount of disorder in a system. When y'all talk about disorder, you have to talk about the number of different microstates, or you have to talk about the total number of possible particle arrangements. Okay? So can I borrow your water bottle? All right, if I have some salts in my hand, just regular table salt, and I dissolve it in water, which one has a greater entropy? The salt in my hand as crystals or the salt dissolved in the water?
Salt in water.
Salt in water. Why?
Because it can be arranged.
It's floating.
Because when you throw them in the water, what happens to those crystals of sodium chloride? They dissociate. So 1 becomes 2. They can be anywhere in this bottle of water instead of being nice and ordered at the bottom of the dish. Right? So we say that positive entropy and positive delta S is more disorder. Now y'all, you're going to get this backwards in your head unless you work at it. More disorder means less order. Less disorder means more order, right? So when you use a double negative and you say it's less disorder, that means it's more order. Okay? A lot of people think, oh, well, entropy is kind of like my bedroom. No. Just because your bedroom is clean does not make it any more ordered. It's just that's the particular set of microstates that your parents like. The pants go in here, not hanging by the door. Right? So we tend to think we make this order too simple, but we want to be thinking about how many different ways can you arrange the particles when we're talking about delta S. Now here's the thing. Nature loves delta S. Nature loves a positive delta S. Nature always wants there to be more disorder. Can y'all give me a reaction that you would call favorable? Something that happens without you having to do a ton to it to keep it going. A chemical reaction that once you get it going, it goes just fine. You don't have to do anything to it.
Burning papers.
Burning stuff. Whatever stuff that is. Paper, wood, whatever. Once you get it going, once you pass that activation energy, remember those? Boom, it just goes on its own. Well, you take a solid, and when you burn it, you release energy. So that energy is no longer contained in that piece of wood. Now it's everywhere. And you turn those solid particles of wood into gases, CO2 and water vapor that go everywhere in the world. That's a lot more disorder just because of particles, right? Nature loves disorder. Yeah, what would you say you are? Are you ordered or are you disordered? You as a human being. I'm not talking about your messiness. Messiness is not a good way to talk about disorder. You're very ordered. If nature had its way, what would you be? Dead. Because when you're dead, what happens to all your molecules that are oh so neatly brought together? And they decompose and turn into largely gases.
Yeah, nature will win.
Right.
Just in case you were wondering.
So your job is you have to overcome entropy to keep things ordered. And to do that, it takes you inputting energy. So you have to put energy into your body. Trust me, not that I want you to try it. But if you just stopped eating, after a while, your body would die and become disordered because you are no longer putting in energy to maintain that order. Okay? All right. So nature wants there to be more disorder or a positive delta S. All right? So, with 4 dots in 2 boxes, I can create lots of different possibilities. Y'all buying those possibilities? Right? Okay. So, I could increase the number of dots, or I can increase the number of boxes. Each possibility is a microstate. This has a possibility of 16 different microstates. I can increase the number of microstates by adding more dots and making there more boxes for them to have to go into. Right? It's just a possible number of microstates. Right. This is the graph that we looked at before. Cold gases, warm gases, hot gases. The hotter you get, the total number of possible microstates increases. You can have some that are going very slow, some that are medium slow, some that are average, some that are greater than average, and some that are very fast. But the hotter they get, the greater the possible number of microstates. Right, so y'all turn and talk to each other real quick. Positive delta S or negative delta S for each one.
Yeah, but the delta, so it's getting more,
Told you.
like this, so it's positive. The negative delta S that's going from gas to solid. Then gas.
And then
Liquid. Negative. And then it's going from 2 to 1, so that's more order. So
You're looking at the state it's in. Okay.
well, it's 3 to 2 actually, not 2 to 1, but still.
Yeah,
yes.
you're right, yeah.
All right, so what do you think of the first one?
Positive delta S.
Positive, more disorder. We're going from a solid to a gas. The second one, not only you're turning a gas to a solid, but look at the number of molecules. That helps too. You're going from 2 molecules in the second equation to 1. Right? That's more order. And the third one, you're taking 2 gases and making a liquid. Much less disorder or more order. And you've got 2 molecules becoming 1. And then, since they're all gases, we just have to do it based on the number of molecules. So you've got 3 molecules over here turning into 2 molecules, and this 2 molecules just seems more ordered. That reasonable so far? Okay, cool. Now, we can calculate delta S a couple different ways. And this will seem very, very familiar to you. And if you look on your sheet real quick, on your reference sheet, see if you can find a section called thermodynamics.
I had you.
And I think y'all did this with delta H's before. So you can, to find delta S, you can take the delta S of formation of all the products minus the delta S of formation of all the reactants. Does that seem fairly familiar? Right? If they gave you these numbers, we could do that math. And the math ends up to be negative 188. Now, I've seen that y'all can use a calculator today and y'all can do some math, so I'm not worried about y'all doing the math. Okay? Now, here's something I want you to notice. What are the units of delta S?
Joules per Kelvin.
Joules. What are the units of delta H? I know it's a long time ago, but kilojoules. Have y'all had success just slapping numbers together in the past without worrying about units? How's that worked out for you? Not very good at all, right? So we're going to have to pay attention to the units as we do some math. Right? So assuming we can do that. All right. Gibbs free energy, which we call delta G. Now, we used to call this spontaneous. When I say a reaction is spontaneous, what does that sound like to you?
It just happens.
It should just happen. Is paper burning spontaneous? Yes, it is. If I get it hot enough, it happens on its own. So this thing should burn if I get it warm enough. If I get the activation energy right, this will burn. And you don't have to go back. Try burning your house down someday. Start it on fire. See if later you have to come back and re-catch it on fire. You don't. You don't have to start with a piece of paper and come back later and light it on fire again. Light it on fire. Once it goes,
Atticus, don't try it.
it goes. Yes, please.
Avoid those Christmas paper plates. They catch fire in the microwave.
How do you know that?
Because it's happened twice this week to us.
Why do you think he knows that?
See, my question is, why are we using Christmas paper plates?
Because my wife,
In April.
she loves the clearance aisle at Walmart.
Yeah?
Yeah.
It's cheap.
Okay. Well, the good news is, if you ever start a fire in your house, like the fireplace or whatever, you just pop one of those in the microwave, then run it over to the fireplace.
Times get tough. I know how to get an insurance claim.
Right, okay. No one heard that at all. All right. Now, Gibbs free energy tells us whether something is thermodynamically favorable or not. We don't use spontaneous anymore because spontaneous is not right. Thermodynamically favorable means, does the universe think it's okay for that to happen? So thermodynamic favorable reactions happen on their own once you get them started. So what's a lab y'all did last semester? Did you add, or at some point in your, did you drop a metal in some acid at some point?
Yes.
Did it happen? Did it fizz?
Yes.
Thermodynamically favorable. Because it gave off bubbles, gas, and it got warm. Nature loves fire. That's why fires happen. It's hard to put them out. Thermodynamically favorable is fire. Negative delta H, thermodynamically favorable. Positive delta S, thermodynamically favorable. Always. That's why fire is a wonderful and a not wonderful thing, just depending where it is. Thermodynamically favorable says this should happen. Now, it may not always happen just because maybe it's too cold. Does gasoline burn? Sure it does. So if I put some gasoline on the table, is it going to burst into flame? Like, you ever pump gas into a car and it just catches fire right there because you put gasoline in there? No. It takes a spark to make it happen. It's thermodynamically favorable that it will happen. You just have to give it the activation energy to make it happen.
Can I ask a question about this?
Sure.
Is this in terms of chemical reactions, or can physical changes be described in this way?
It's either physical changes. So it's either a phase change, a physical thing. Could be something dissolving.
Gasoline going to a vapor, thermodynamically favorable?
Right, and it does happen.
Yes.
Yeah. So it could be a change of state. It also could be something dissolving. Like, so, cup of water, salt, let it stand. Will the salt dissolve after a while?
Yes.
Sure. Because you're taking a solid, you're turning into ions. Entropy is increasing. Right? Now, the delta H, I don't know, because I never stick a thermometer in salt water, but sure, we could do some math if we want to do. All right? Now, the thing is, what if they're both not something nature wants? What if it's negative delta H, but also negative delta S? What if it's putting out heat, but creating more order? Then how do you decide who wins? What if something gets colder, and yet there's a lot of entropy? How do you decide which one wins? So I want you to find this equation on your reference sheet. The relationship is delta G is equal to negative delta H minus T delta S. So plug in some numbers with me in your head real quick. If I plug in a negative number here and a positive number there, what sign is the answer always going to have? If I plug in a negative number for delta H and a positive number for delta S, no matter what the temperature, what is my answer always going to be?
Negative.
So negative delta G means thermodynamically favorable. If you calculate a delta G and it's negative, boom, that thing is thermodynamically favorable. What do you think happens when delta G is positive? It is not thermodynamically favorable. So negative delta G, thermodynamically favorable. Positive delta G, not thermodynamically favorable. Can y'all tell me the opposite of your house burning down?
It builds itself.
Building a house. So imagine a place where you burn your house on fire, and then you're like, I'll just wait till the winter when it's cold and the house will rebuild itself. No, that is thermodynamically unfavorable. If that was the world, then wow, that'd be great. But, such is life. So that's negative delta G, thermodynamically favorable. Positive delta G, not favorable. What other possibility is there? Negative, positive?
It's like at some temperatures.
Mm-hmm. Well, yeah, we'll get there. But you can have negative delta G, positive delta G, or
Nothing. Zero.
Zero.
what if delta G is 0?
Is that unequal?
Nice. The forward reaction is not favored. The reverse reaction is not favored. Both reactions are equally favored, which means you're at equilibrium. So when delta G is negative, thermodynamically favorable. Positive, thermodynamically unfavorable. Delta G is 0, you are at equilibrium. Okay, we already said burning stuff is thermodynamically favorable. Is this thermodynamically favorable? Well, delta H is less than 0. What does that tell you when it's less than 0?
It's negative.
The negative value. What's happening to the entropy here?
It should be.
Positive delta S or negative delta S? Positive?
Because you're going from 6 moles to 7 moles.
You're going from 6 molecules or 6 moles to 7 molecules. So you're increasing the number of molecules, increasing the number of possible microstates. Okay, what happens when it's negative delta H, but it's negative delta S? Then it becomes temperature dependent. You're fighting entropy against enthalpy. Somebody's going to win, and since it's T delta S, the temperature could be high enough that it makes a difference. Okay, so there's a fancy little graph in here somewhere, which y'all can take a picture of, or whatever makes you happy. Draw it out, whatever makes you happy as a person. It's called always high, never low. And if you draw it out, make sure that you get the x-axis is negative delta H, I mean, the x-axis is delta H and the y-axis is delta S. So nature loves it when things get hot, negative delta H, and things get more disordered, positive delta S. Always thermodynamically favorable. If you can make nature happy twice, then it's always going to be thermodynamically favorable. What's the opposite of that?
Things getting cold.
Things getting cold, so positive delta H,
And more order.
and more ordered, or a negative delta S. And anytime you're trying to say no to nature twice, then that's never going to happen. Thermodynamically favorable, and yet here you stand. Why can you exist? You are more ordered, and you absorb energy. You are endothermic. I know you're like, no, we give off body heat. That's only because you eat. You have a positive delta S for life, and you have a negative delta S for life. So thermodynamically favorable says it's not going to happen unless you force it to happen. There has to be some input of energy to overcome the thermodynamic unfavorability of it to make it happen. This is true for trees. Trees breathe in CO2 and make wood. Thermodynamically unfavorable. They take gas and turn it into solid particles. They take sunlight and store the energy. They're endothermic. So the only way photosynthesis works, it's a thermodynamically unfavorable process. But we can force it to happen by applying enough energy to overcome the chaos. So the high refers to at high temperatures. This is thermodynamically favorable. So delta S is positive. Yay, says nature. Delta H is positive. Boo. As long as the temperature is high enough, the temperature times the delta S. As long as the temperature is high enough, the delta S can overcome the delta H.
So is this the example of the piece of paper not catching on fire?
No, because the piece of paper not catching on fire is always thermodynamically favorable. It's just a matter of activation energy, getting it warm enough to actually catch fire. This would be something that
Doesn't that make it temperature dependent?
No, it's thermodynamically favorable. It can burn at any point in time.
It's like once it is burning, it will stay.
Right, once you reach that activation point, it'll go, but you got to get it over that hump. I can apply an enzyme to
So when
make
you
that.
say-
I can apply an enzyme to make that thing happen at room temperature. That's what happens when you eat food.
So when you say temperature dependent, you mean the environment has to stay at a particular temperature?
If the temperature is high enough, then the increase in entropy can be big enough to overcome the positive delta H. Because these two things are always warring with each other when they're at odds. When they're, nature likes this but doesn't like this. Well, if you get the temperature high enough, these two multiplied together can overcome this delta H to make the overall answer negative. Whereas at low temperature, the delta H, nature said, yeah, give me some low, negative delta H. But then it says, yeah, but it creates more order. I don't like that. Well, as long as the temperature is low, the effect of the entropy is low. If this is 5 and this is 5, then the answer is 25. If this is 5 and this is 500, then this becomes 2500. It has a much bigger effect since you're multiplying them together.
And this is in order to get a positive delta G?
Well, depends what you're looking for. If we're trying to make it thermodynamically favorable, then we want delta G to be negative. So we're trying to get delta G to be negative in this whole graph. Right. Can y'all take the delta H of something and subtract the delta S of something? Can you do the equation delta G is equal to delta H minus T delta S? Can you plug those numbers and solve? Sounds pretty easy. 25 degrees, we got to change it to 298 because it's got to be in Kelvin. Good enough. So it's 180.7 kilojoules, and this is 24.7 joules. Oftentimes AP will give you two numbers and say, is it thermodynamically favorable? So, who has made tons of mistakes with units in their past? A couple of y'all, good. Here's the best part. Let's say that you did the math and you got a positive number because you forgot to make it kilojoules. And you were like, it's thermodynamically unfavorable. You would get the point for realizing that positive delta G is thermodynamically unfavorable, even though you screwed up your calculation. Someone over here that doesn't make mistakes, they will tend to get the right answer and then say it's thermodynamically unfavorable. Because you did the right math, you did the unit change. What I'm saying is, if you do math wrong, and then you use that to answer a question later on, you could still get the point, even though you're wrong.
If your reasoning about your incorrect math is legit, you get credit.
It's called double jeopardy. Right? So, assuming y'all can change the number to Kelvin, and plug and chug, and remember that joules have to be changed to kilojoules. That sound reasonable? Okay. So, let's see. No. All right. Have y'all seen this before?
No.
Have you seen something like it before?
Yeah.
Like it before.
Wasn't there a delta H where you took all the products minus all the reactants? Didn't we just show you one with delta S was all the products minus all the reactants?
Yep.
And isn't this equation also on your reference sheet? Under thermodynamics. Right? Okay. So far so good. All right, now. What does a K of 1 mean?
With no favorable sign. Because it's products over reactants.
So at equilibrium, products and reactants are equally represented. A K of 1 means you got an equal amount of products and reactants. What does a big K mean? What's a K of 1,000,000?
More product.
Product
A
favor.
lot of products. So would you say when you have a lot of products that the forward reaction is favored? Because you're making a lot of products. Okay? And what is a K of a very small K, like 0.0002? So the forward reaction, since it's staying reactants, the forward reaction is not favored. In fact, the reverse reaction is favored. So this combines the idea of equilibrium and delta G. Delta G is equal to negative RT ln of K. Now, ln, natural log. You all have this button on your calculator, right? Let's say we plug in a K of 1,000,000. Is the natural log of 1,000,000 a positive number or a negative number? Natural log of a big no, without using a calculator. Is the natural log of a big number positive or negative? It's positive, because we're thinking about exponents, right? So any number greater than 1, the natural log of it is a positive number. Any number less than 1, the natural log of it is a negative number. So the natural log of any number greater than 1, positive. The natural log of any number less than 1, negative. So what's the natural log of 1? 0, because e to the 0th power would be 1. So we can kind of frame that out in our head. All right, so if K is 1,000,000, natural log of it's going to be a positive number. R, which R do we want to use?
Not the ideal gas law one that you guys used.
There's
in
a
that.
bunch of them. Let's look on our sheet, figure out which R we want to use.
The 8.3
There's
one.
like 2 or 3 of them.
It's not there.
That one.
It's on the side with gases, liquids, and solutions in that far right-hand column.
The way you would know is it's got joules in it, and we're talking about energy.
Right? We don't want atmospheres, right? We don't want millimeters of mercury or anything like that. Since we're talking about kilojoules per mole kind of stuff, we want to see the one that says joules. Right? So we're going to use that 8.314. So you get negative 8.314 times some number. Temperature has to be a positive number because it's Kelvin. So it's a negative times 8.314 times a number times a positive number. A negative times a number times a number times a number is always going to be a negative answer. So when K is greater than 1, delta G is negative or thermodynamically favorable. The natural log of 1 is 0, and a bunch of numbers times 0 is 0. So that's where we get this thing right here. Now, how is that going to show itself on the AP exam? Usually it's something like, here's a delta G value, find the value of K. Now, what's the trick? She's gone, so let's ask you. Give me a number.
Any specifications?
Nope.
Okay. 4.
4, positive or negative?
Negative.
So the delta G is negative 4 kilojoules per mole. Find the value of K. Let's do that. The delta G is negative 4 kilojoules per mole. Delta G is negative 4 kilojoules per mole. Find K. Let's see how that works out. Go ahead and use the equation. Let's see what we can do.
At what temperature?
Oh, yeah, we need a temperature. Temperature.
298. It's a good one.
298.
298. Okay, at 298 Kelvin. 25 degrees. So let's see if we can find the value of K. For some of you, it's been a long time since you did an inverse natural log. So on your calculator, you want to find the LN button, and you want to push the second LN function to kind of do an inverse natural log.
Is that just LN? Is that just LN?
You made it 27? Meaning, all right, just check it.
I forget how to do it. Yes, I think it's 5.03. I think what you have to do is do all the algebra and then raise that fraction to e raised to that fraction is what I think it is. So what I'm saying making sense, like e raised to delta G over R T equals K. I don't know if that's right.
You got to be able to take that answer and just do an inverse natural log.
What is that? I guess, but okay.
Whenever I multiply.
Why does he have Kelvin on there twice? That's what I'm wondering.
Where?
298 Kelvin times Ln Kelvin.
No, that's K. That's a K constant. You
Okay.
can put a little subscript C there if you want to keep it
the temperature
straight.
is the okay.
Yeah,
Okay.
yeah. Just put your little sub K constant there.
Okay.
These have started disappearing from the exam because at this point it's just mathematical manipulation. It doesn't really have any meaning.
Yeah,
But
yeah.
occasionally you'll see like on an FRQ that's like, find K, you know, or they give you a K and then say find delta G. So,
So I don't know if I did the algebra right, but
we shall see in a minute. Does anybody have an answer they're willing to share?
I got 1.0.
no, I got 5.03.
What'd you get?
I got like a long decimal.
Okay.
I got one.
What'd you guys get?
What'd you get today?
Okay, all right. I got what you got,
Are we
but-
finding
Okay.
Ln? I have a hard finding.
You know what's crazy is the numbers that we made up are super close to the golden ratio.
Oh, we're finding
It's
the
like one,
constant.
1.617.
Okay.
But then you have to e raised to 1.617.
All right.
I don't know.
You guys got 1.0. Did you change the negative 4 kilojoules per mole to joules per mole when you did their math? Because you have to remember the 8.314 is joules per mole Kelvin. And this one's in kilojoules per mole. So if you got 1.0, I think maybe you didn't change this. This should be negative 4,000 joules. And
Just to
I
get the, just to get the
5.6.
units in joules.
I changed it to the 8.314 to kilojoules. Does it
So delta G
I can see
should
what
be
you did.
in,
Yeah. Wait,
like
which
it
one
was given to us in.
The 5.2. Yeah, then that's right.
No, delta G was given to you in kilojoules per mole.
Okay.
But K is in, no. The,
You have to be able
so it
to-
doesn't matter. We just got to get the units either both joules or both kilojoules.
Right, it doesn't matter which one you change.
Because those units cancel. Because K has no units. So the units just need to both be coherent.
Right, so this is where I solve for ln of k is equal to. That's what I got.
Okay.
So if you can get to that point by taking negative 4,000, dividing it by negative 8.314, and dividing it by 298, that's what I got for ln of k. And then you have to force your calculator to do this. E to the 1.614838858. And I did that by adding second in ln. And I got an answer of around 5.
You should get like 1.6.
All right, so what does nature love?
Disorder.
Entropy, disorder, and heat being given off, exothermic, right? Those will always be thermodynamically favorable. Use that equation, delta G is equal to delta H minus T delta S, probably 90% of the time to solve these problems. Okay? That is entropy and stuff like that. Make sense? All right, let's go on to cell phones. Did y'all do redox reactions at all?
Yes.
Okay. So, can y'all remind me what oxidation is?
The yeah, so electrons are added, so it's reducing the charge.
No, it's no. Oxidizing something is
Lowering.
taking away
Oxidation.
electrons, making it more positive.
Reduction is gain.
Reduction is
Yeah.
making something more
Yeah.
negative by adding electrons.
Okay, Leo, the lion, says grrr. Leo, losing electrons is oxidation, says grrr. Gaining electrons is reduction. Right? So you could do a redox reaction in a flask, and that's fine. Or you can make it do some work for you. What if on one part of your phone something lost electrons and we made them travel through wires, and then they got to the other side and something gained those electrons? That would be called electricity. So a battery is nothing more than a redox reaction, where something is losing electrons, they're traveling through a wire, and we're using that to power our phone. What do you call it when your phone is out of those electrons? A dead phone. And when you've moved all the electrons from one side to another, what do you have to do?
Add electrons to it.
You have to add enough energy to move those electrons back to the other side. And we
Yeah,
call that-
electrons aren't lost.
Right, yeah.
They're not lost.
Right. They go from one part of it. One chemical loses the electron, another chemical gains them. And once you're out of all the transfers, you got to make them all go back. And that's called recharging your phone. Which one would you say is thermodynamically favorable? Your phone working all the time or charging your phone? Working. Because what do you have to do to it?
Charge it.
No, just to make it work.
Put energy in.
Nothing.
Just use it.
Nothing. It's just
Use it.
there doing its thing.
Energy in it.
Is your phone charging thermodynamically favorable? Does it just happen on its own? If only. Right? Oh, my phone's dead. Just give it a while. Nature will just make it recharge on its own. If only that were the case. What a great world that would be. So, a battery, thermodynamically favorable. Charging a battery, thermodynamically unfavorable. Right? So, electrochem is just exactly this idea of using these electrons. So, we already talked about that. Which of these show reduction happening?
One and three.
1 and 3. Because reduction is gaining electrons. The other two are oxidation. Good. All right. All right. So assuming you all know how to do that. All right. There's two types of electrochemistry stuff. One is called a galvanic cell. That's probably a word that y'all are not used to that we probably ought to write down. Galvanic means it's a battery. So this is a battery working as a battery. Galvanic cells are the ones that are thermodynamically favorable. It's a battery. Electrolytic cells require a power source. So that's like charging your phone. So galvanic cells is like a battery. Could be a double A, could be a triple A, could be one of those D cells or something like that. We're going from chemical energy to electrical energy. Electrolytic is the exact opposite. So, electrolytic cells have a power source. They require a power source to work. Galvanic cells just work. All right, so we've got some vocabulary we need to know. Anode, anox. Anode is where oxidation happens. So the anode part of the battery is where oxidation happens, where electrons are being lost. The cathode is the exact opposite. Anox, oxidation happens at the anode, reduction happens at the cathode. So just like there's two ends of a battery, right? There's a positive and negative end. One of those is an anode, one of those is a cathode. Electrons always flow alphabetically. Electrons are always going to flow from the anode to the cathode. So anode oxidation, cathode reduction, electrons always flow from anode to cathode. What does that mean? They may have you label it. They may say, hey, here's the anode, here's the cathode, draw an arrow which way the electrons go. Or maybe they have a direction the electrons go and they say, hey, can you label the anode and the cathode? But we always flow from anode to cathode. And I'm assuming y'all have heard the word volts before. The Chevy Volt comes to mind. What's another volts you know? Or how many volts is this wall plug? Do you know?
They don't know that.
Okay. Well, you never know what somebody. So these are about 110 volts. If you were in Europe, they'd be about 220. This thing that charges my computer, the USB thing that you can charge your phone with, is 5 volts. So a volt is just a unit that tells us something about electrical energy. So far, so good? Okay. Right, now, what happens if you have a cell and all the electrons are going from one side to the other? What happens over time is one side gets crazy negative and one side gets crazy positive. And if the crazy negative side, if the electrons try to get into the negative side, how do electrons feel about each other? So at some point, this thing can become so negative that as the electrons try to cross over here, they can't anymore. So to provide a way for things to kind of balance out, charges to balance out, we're going to provide something called a salt bridge. And I got a picture for you. So the electrons are flowing from the piece of zinc over across through the wire and down to the piece of copper. They're flowing from anode to cathode. What's happening at the anode? Oxidation. So we have things losing electrons. Okay? Now, the electrons are going to build up over here, creating a negative charge. So what we've done in our salt bridge is we've added a solution that's not going to affect it, but a solution of ions that can travel. Well, if you've got a bunch of negative charges over here, who's going to move over there? Is it going to be the positive sodium ions or the negative chloride ions? If this thing is really negative, who's going to move over that direction? Positive ions. Are you sure? Yes, I'm positive. All right? And if this guy is losing negative charges, then he's becoming, or she's becoming, he's becoming, they are becoming very, very positive. So which kind of ions are going to move over this way? The negative ion. Now, what would happen if you didn't have a salt bridge to equalize that charge?
It would just stop flowing.
The battery would stop flowing. So sometimes the question is, what happens if there's no salt bridge? The voltage is 0. Things just stop. Okay. Now, notice that what we have here are two half reactions. We've got the zinc metal becoming zinc ion. I know it's kind of hard to see down here, but you got zinc metal becoming zinc ion. It's losing electrons. So what's happening over here? The copper ions are gaining electrons and becoming copper metal. What happens to the piece of zinc over time? Should the piece of zinc over time get bigger or should it get smaller over time?
Smaller.
Should it get smaller because we're turning those zinc atoms into zinc ions. And there you go. What should happen to the piece of copper over time as those copper ions in solution gain the electrons and become solid copper? Should get bigger. So far, so good? Okay. Negative delta G or positive delta G? Do you see a power source? No.
So, negative.
Negative delta G. Thermodynamically favorable to the battery. Galvanic cell. It happens. Right? What would have to happen if we wanted to cause the electrons to go back the other way?
You have to.
Add positive things.
We'd have to add voltage that's greater than 1.1 to overcome the natural flow. We have to apply a voltage that's greater than 1.1 to cause it to go back the other way. All right? So, diagram of the cell is pretty easy. All right, so let's look at this. The way they've listed both the reactions, they're both reduction. What's the problem with both of them being reduced?
Electrons aren't really going to one place.
Right. For every oxidation, there has to be a reduction. For every reduction, there has to be an oxidation. If I go and lose money at a casino, then somebody else has got to be gaining said money.
They're just taking electrons from nowhere.
So these half reactions are written in what's called standard reduction potentials. So this is the volts that are necessary to make these things gain electrons. If we flip this reaction to be where it loses electrons, because in our example, that's what happens. The zinc gave up electrons. If we flip it, guess what we have to do to the sign of E naught? E naught means the electrode potential, the volts at standard conditions.
Change it.
We have to flip the sign. So if we flip the equation, this becomes 0.76. Easy enough? Okay, now here's the thing, and I don't want you to hurt your head. Because of the weirdness of volts, if you double the reaction, you don't double the number. Okay? So if you have to multiply an equation by 2, you don't multiply the voltage by 2. This is very wrong in so many ways, because up to now, we've taught you so many times that if you double an equation, you have to double the delta H or something like this. The idea here is the units are something called a joule per coulomb for volts. If you double the reaction, you double the number of joules, but you also double the coulombs. So it works out to be the same since it's joules over coulombs. Not that that's important. But if you multiply an equation, you don't multiply the E. All right, so all you have to do is to find the E of the whole cell is you got to flip one of them and then you add them together. That seems easy enough so far. Flip one of them because they're both showing reduction, add them together. So we flip this one, and we'll tell you how to know in a minute. We flip this one to be positive 0.76. Positive 0.76 and a plus 0.34 is 1.1. And what did the voltmeter on the picture show you? I showed you and say
1.1.
1.1. All right. Now, all right. So here's the key here. For thermodynamically favorable things, for galvanic cells, E has to be positive. For galvanic cells, E has to be positive. For electrolytic cells, E has to be negative. So very easy here. We have to flip one of these. Is this a power source? A light bulb? Is that a source of power? No. We're trying to light the light bulb. So since there is no power source, this is a galvanic cell. We want the E to be positive. So you have to flip one of these and add them together to get a positive number. I'll let you think about that for a minute. Which one do you want to flip so that when you add them together, you get a positive number? This one. Okay. So that means we flip this one. So the zinc is going to become zinc plus, okay. So, which one is the anode?
The right side.
This side? So the zinc is the anode because
It's being oxidized.
when we flip it, it's not being reduced, it's being oxidized. So anode, which makes the other one cathode. Do the electrons go left to right or right to left? Right to left, because always from the anode to the cathode. So far, so good. Calculate the standard potential. Well, that's easy enough. Positive 0.76, negative 0.25, positive 0.51. E is 0.51, right? Write the balanced net ionic equation. Well, when you flip them around, the nickel ions plus the zinc is going to make just nickel plus zinc ions. Sorry, the nickel ions plus the zinc is going to make zinc ions plus the nickel. Flip them, add them together, easy peasy. Yep, all right. Describe how the K ions will move from the salt bridge. So, which way did we say the electrons are going to flow?
Right.
So the electrons are going to flow over here. So which side is going to get more and more and more negative? The left-hand side, because we're getting all these electrons over here. So which way are the potassium ions going to be attracted? Are they going to go right over to this beaker, or are they going to go left over to this beaker? They're going to go over here. The positive ions are going to follow the flow of electrons. Doesn't that kind of make sense? Okay, good. What is the E naught without the salt bridge? Zero, because it ain't going to work. What's hard so far? Nothing. All right, okay, that was the right answer. This is why I didn't start with this and then end with buffers, because I could just see y'all going. Right? All right. All right, now, I want y'all to think about this for a second. Y'all have heard of the word, actually, just, let's not even do this for a second. Don't pay attention to this. It's just going to hurt your head. If it's on the AP exam, it'll be 1 point, so we're not going to worry about it. Have y'all heard of volts? Yes. You ever heard of something called an amp? Okay. So, what is an amp to you?
Like amplify something.
Well, yes, you can have an amplifier, but an amp in terms of a unit. You guys ever heard of that? It's okay if you haven't. So, okay. So, what I want you to think about is voltage is how fast water comes out of a hose. So, put your finger over the end of a hose. Voltage is how fast it sprays out of the hose, right? Amperage is how much water is moving through the pipe. So, you could take a tiny little hose, put your finger over it, and get the water to squirt out fast. You could take a great big honking 1 foot around pipe and take a really big thumb and put it over it, and it would squirt out fast, right? You could get the same voltage, but vastly different amperage, right? Okay, so let's keep this in mind. Does anybody know the voltage of your gasoline burning car? This used to be so much easier before EVs. Yeah, gasoline burning car, the battery in your car, 12 volts, right? 12 volts. How many amps is it? 70 to 100. The voltage isn't as important as how many electrons you can flow. Next time you open up your car hood, which you should all do at some point, I want you to notice the wires on the battery. They're not these tiny little Christmas strand lights. They're these great big honking wires because they have to carry a lot of amps, right? That's 5 volts in there, and it's probably about 10 microamps or milliamps. It's a very low amount of amperage. Okay, so how many volts is a AA battery? Does anybody know? 1.5, a volt and a half. If you have 9 volt and if you have 8 1.5 volt batteries hooked up a special way, how many volts do you get out of them, do you think?
12 for one.
12 volts. 8 times 1.5 is 12. Carbon. 9-volt batteries. Y'all have seen the 9-volt batteries? They have the 2 knobby ends on them. Look kind of weird. That is 6 1.5-volt batteries just hooked up together. How about a AAA battery? How many volts is that? AA, 1.5 volts. AAA, 1.5 volts. Same voltage. How about a D cell? Maybe you've seen your parents have this old flashlight that doesn't work anymore, but they keep it around anyway. The batteries are like this big. They're a huge honking thing. How many volts do you think that is? 1.5 volts. How about a C cell? A little bit smaller. Anybody got a guess? 1.5 volts. So what's the difference? The amount of electrons they can carry. In other words, the amperage. So why don't we use, in a TV remote control, why don't we use D cells? Like you could put 4 D cells in your Roku remote. What would be wrong with that? It's huge. No, it's not. It's not too many amps. It'd be huge and heavy and not sleek looking. But man, it would last forever. So why not use tiny AAAs in a heavy duty flashlight? It would work. It just wouldn't last very long. The more chemical you have in there, the longer it can provide that voltage. Right? Now, your car battery is 12 volts. When you go check your car battery, how many volts did it have? More than 12. And here's the reason. 12 volts means you have an equal amount of reactants and products. In other words, at standard conditions, you have an equal amount of products and reactants. Everything's 1 mole. But the problem is, you don't want equal amounts of products and reactants for your car battery. Your car battery, you want it to have way more reactants than products, because you want that reaction to last for a very long time. So if you take your car to have the battery tested and it says 12 volts, something's wrong. You want your car battery to be farther away from equilibrium. You want that car battery like 14 volts. That shows you got way more reactants and less products, right? And then as time goes on, the voltage gets lower and lower and lower. You go from 14 volts to 12 volts to 11 volts, and past about 10 volts, your car battery just doesn't work anymore. Doesn't have enough oomph, right? All right. So, for a galvanic cell, we want a positive E, and we want to be able to calculate delta G. So here's the calculation. This is on your sheet as well. Can y'all find the delta G for the reaction that we just did? Y'all remember what the E was for that cell? Where we had the 0.75 and the 0.21 and all that kind of stuff?
1.1.
Okay. I think this is what you call 0.51, right?
0.51, yeah.
0.51. All right. E is 0.51 volts. Can you find a delta G for that? Well, let's think about that for a second. N is the number of moles of electrons. So if we go back, how many moles of electrons were being transferred in that thing before? 2. So our moles of electrons is 2. What if this reaction had said 1 electron? Then to get everything to work, we would have to multiply this equation by 2, wouldn't we? Right? But what would we do to the E if we multiplied it by 2?
Nothing.
Nothing, right. Okay, good. But, so we've got 2 moles of electrons changing hands. N is 2. The voltage is 0.51, positive 0.51. And see if you can find F somewhere on your reference sheet. Faraday's constant. And see if you can do that calculation. It's just 3 numbers, negative N times F times E. And be thinking about units one more time. And let me tell you that a volt is the same thing as a joule per coulomb. And it says that on your sheet. A volt is a joule per coulomb. soon as anybody gets an answer they're willing to share, call it out. You may get 31. Me neither. All right.
Okay. It's just 1 times Faraday's constant. They're pretty close to 1, right?
Look, N would be 2 because there's 2 multiple electrons. F would be 96,485 times 0.51. So yeah, close to 1 times that. Yeah.
I got negative 98,414.7.
Yeah.
We looked at this in class before, and I think what screwed us up was when we multiplied an equation by 2, we also multiplied E by 2.
I don't remember doing this in class.
And maybe it was somebody.
Docs or something like that. Sometimes you mix them together. Now here's the problem. Units.
It looks like it's just joules.
It is joules per mole. Joules per mole. What is delta G measured in them? Kilojoules per mole. So on the AP exam, they'll oftentimes say, calculate delta G with appropriate units. If you write negative 98,414.7 joules, that's fine. If you write down negative 98.4 kilojoules per mole, that's fine. But if you just wrote down 98,414 without a unit or the wrong unit, that would be wrong. So, is a G of negative 98,000 thermodynamically favorable? Yes.
Yes.
I would say that's a pretty big number, right? With a pretty big K. All right, so that was galvanic. How do you know if it's electrolytic?
Power source.
Power source. How do you know if it's a power source?
It'll show.
It'll show something plugged in, or it'll say the words power source. Now, this is the exact opposite. What do you think the E of an electrolytic cell should be? Positive or negative? Negative, right? The electrons still flow from anode to cathode. You don't need a salt bridge. So, how do we use electrolytic cells? Well, we use it to charge the cell phone. Here's the other thing you can do. This used to be a big thing, and hopefully no one does anymore. Does anybody's mother have baby shoes from where you were a baby and they had them bronzed? Sounds crazy, right? People used to take baby shoes and they would take the shoes and they would dip them in a chemical bath that actually caused the copper ions in solution to plate out on the surface of the shoes, and you would build up a layer of copper over time. Those are called electrogalvanized, meaning it's electrolytic cells. You're feeding in electrons from electricity. It's grabbing onto the copper ions. Boom, you make copper metal, right? That's how they make chrome bumpers. They take a bumper that's made of steel, and they dip it in chromium ions. They hook electricity up to it, sticks to it, right? So anybody's parents have real silverware that you hardly ever use. It's like a real piece of silver. Like, do you ever use it at all? Why?
I don't know.
Right,
I
but
just
it's
don't use them.
that's right. Because real silverware is really expensive. It's totally silver. Now, how do you make silverware that's cheaper? When you take steel silverware, you dip it into a bath of silver ions, use electricity to stick the ions down to the surface. So really, it's just a thin surface of silver and steel. If you use them all the time, they get ugly looking because there's like smudges on them, and you rub them to get the smudge off. And if you keep rubbing them like that, at some point the silver comes away, and now you have rusty iron. So what's the answer? You take them back to the people that do electroplating, and they dip them in the thing, and they add more silver. Nobody's got time for that anymore. It's just not worth it, right? So we can actually use electrolytic cells to get metals to stick to things. For example, pennies today. What's in the middle of a penny today?
Nickel,
Copper all the way
zinc.
through?
No.
Cheap zinc. So take a penny, rub it against a brick somewhere, you'll see a band of silver in there. That's zinc. Because copper pennies cost more than a penny to make. They realized that back in the 1980s. So they make a zinc penny, and then they use that process of putting copper ions in them using an electrolytic cell. And these hardly ever show up on the AP exam, so I'm not going to spend a bunch of time. All right, now. I'm going to show you this. If you get it, great. If you don't, that's okay too, because I want you all to see some sample questions. You can do stoichiometry with electrolytic chemistry. So, how long must a current of 2.5 amperes, be applied to a solution of silver ion to plate out 11.5 grams of silver? Right? We're trying to put it on your silverware that you never use. Right? Now, what can you do with grams always? Go to moles. When in doubt, mole it out. Grams to moles. So that's going to be our first step. Change grams of silver to moles of silver. Now, if we have the equation, we're changing it from silver with a +1 charge to silver with no charge. How many electrons does it take to go from silver with +1 charge to silver with no charge? How many electrons does that take? 1. Okay? So, we're going to call that, we need 1 mole of electrons for every 1 mole of silver. That makes sense? Because you're just making it change 1 electron. Okay. Then, we use Coulomb's law. Not Coulomb's law. Faraday's constant, which is 96,485, the number I used before. The units of that are coulombs per mole. For 1 mole of electron is equal to this many coulombs. You set things up so that stuff cancels, and you get a number of coulombs. Now, what's an amp? Y'all may have to write this down. I don't remember if it's on the sheet or not. An amp is just a coulomb per second. An amp is how many coulombs per second. How much charge per second is traveling through the wire. So an amp is coulombs per second. So when I was young, we had a hot dog cooker, and I think they still sell them today. You impaled the hot dogs on 2 electrodes. You put them in the electric chair. You put a hot dog on these 2 electrodes. You plugged it in the wall and you pushed the button. It ran electricity through them like the electric chair here in Alabama, and it heated them up till they were real good and sizzly and started to rip open. We thought that was awesome, right? So you could, I guess, calculate how many coulombs it took to do that. The more amps you put through them, the more coulombs per second. So if y'all solve for the number of coulombs, then 2.5 amps is the same thing as 2.5 coulombs per second. So 2.5 amps is a certain number of coulombs per second. So if you know the number of coulombs, can you solve for the number of seconds?
That equation on there? Yeah.
Okay, and that seems pretty reasonable.
Charge over time is all it is.
You also could have done the math right here. You could have substituted right here by putting times 1 second over 2.5 coulombs. Because remember, an amp is coulombs per second. So if you had 2.5 amps, you could have said times 1 second over 2.5 coulombs. You still get the right answer. You could do it all in one fell swoop. Like I said, that might be one question, so we're not going to worry about it. So the question is, what can y'all expect in terms of AP exam? I always like to look at the most current. All right, a table of absolute entropies of some substances is given below. Explain why the entropy of silicon is less than the entropy of hydrogen.
Because the solid is in fixed position.
It's a solid, so
Its particles are not, they're fixed.
they can't reproduce like a
Like-
dog, fixed like a
No,
dog.
like they're fixed in a held position, like there's not, you said,
You're not using the verbiage I'm asking y'all to use to talk about entropy. That's why I'm poking at you.
Is that phrase in particular you used earlier, the
That's
language
gotta
that
be
they
the one they
So that's
use.
possible microstates.
yes, that's what I'm.
For which one?
For, silicon.
Silicon being a solid has fewer number of possible microstates. Or particle arrangements, you could also say it that way.
Yes.
Has a fewer number of possible particle arrangements, because they're all a solid together in one spot. Hydrogen's a gas, so it could be like anywhere in the room, versus silicon, like in a pile at the bottom. So hydrogen has a greater number of possible particle arrangements or microstates. Either one will get you the point. But you can't say it has more disorder, because you're just saying, I know what entropy means. Right? They're asking you to carry it a little bit farther forward. Calculate the value of delta S for the reaction. Ooh, I didn't pull the reaction. That's my fault. All right, so gotta fix that tonight. If they give you these and they ask you to find delta S, can you find the delta S of all the products minus the delta S of all the reactants? Okay. Yeah, so that's something I will fix tonight. Can you put it back up there? The reaction is thermodynamically favorable at all temperatures. Explain why the reaction only happens at high temperatures. It's thermodynamically favorable. So why does it only happen at high temperatures? Yes, it's like the paper burning.
What's the verbiage?
Y'all did kinetics, right? So what does it take to make a reaction happen?
Activation.
It doesn't have an activation. It's got a high activation energy, right? But then at that point, it is thermodynamically favorable. Good. All right. So is this electrolytic or galvanic?
Electrolytic.
How do you know it's electrolytic?
Says power source.
Because it says power source. How do you know it's a power source? Because it says power source. You're right. Very good. All right. Draw an arrow on the diagram to show the direction of electron flow through the external circuit as the cell operates. They're both reduction. We got to flip one of them.
The
What do you want the E
sorry, I was talking.
of an electrolytic cell to be? Positive or negative?
Negative.
Just far too negative. Right. So which one are we going to flip so that when we add them together, the answer is negative?
Second one.
The chlorine. So this one we're going to flip. So the chlorine won't be reduced anymore. The chlorine will be oxidized. And the magnesium will be reduced. Draw an arrow to indicate